Hello and welcome to this lesson on functions integration with OCI services. My name is Mahindra Mehra and I am a senior OCI instructor with Oracle University. In this lesson, we'll explore the integration of Oracle functions with other Oracle Cloud Infrastructure services. Additionally, we'll explore how to access other OCI resources from running functions. So let's get started. First, let's discuss how functions can be triggered. OCI offers several services that can automatically trigger functions for you. These includes the event service, which can invoke functions in response to specific events, and the API gateway, which can expose your functions as API endpoints. Additionally, you can manually trigger functions using the CLI and the SDK, giving you flexibility in how and when your functions are executed. Once a function is triggered, OCI functions pulls the corresponding Docker image from the OCI registry and starts the function container. This allows for efficient and scalable execution of your code. While your function is running, it has access to a wide range of downstream services. For example, your function can interact with object storage to read or write data, connect to an autonomous database for advanced data processing, or leverage compute resources for additional computational power. It can also securely access sensitive information using the secrets service, manage networking configurations, and much more. All the logs, metrics, and traces generated during the function execution are automatically sent to OCI's logging, monitoring, and application performance monitoring services. This integration ensures that you have comprehensive visibility and insight into your function's performance and behavior, helping you maintain and optimize your applications effectively. With these integrations, OCI functions provide a powerful platform for building, deploying, and managing serverless applications that can interact with a wide array of cloud services, ensuring your solutions are both flexible and scalable. Let's take a look at the steps required to enable a running function to access other Oracle Cloud Infrastructure resources. To begin with, we must create a dynamic group for the functions. It totally depends upon your use case. If you want all functions in a compartment to be able to access a resource, enter a rule similar to the following on the screen. This rule adds all functions in the compartment with the specified compartment OCID to the dynamic group. As you can see here in this example, the dynamic group name is Acme function dynamic group, and we are adding all the functions in the resource.compartment ID whose compartment OCID we have specified in the dynamic group rule. If you want a specific function to be able to access a resource, then you must enter the rule as displayed on the screen. Here you add the function with the specified OCID to your dynamic group. And the rule is resource.ocid and specify the OCID of your function. And if you want all functions within a specific defined tag to be able to access a resource, then you must enter the rule as displayed on the screen. For example, if you want to specify all the functions with a specific tag in your dynamic group, you use the rule all resource.type, which is set to fn function, and specify the tag name and value. Having created a dynamic group that includes the function, you can now create a policy to give the dynamic group access to your required OCI resource. If you want your function in the Acme function dynamic group to be able to get a list of all the VCNs in the tenancy, you must specify the following rule, which allows your dynamic group Acme function dynamic group to inspect VCNs in tenancy. If you want a function in the Acme function dynamic group to be able to read and write to a particular object storage bucket, then you must enter a rule similar to the one given on the screen, which allows your dynamic group to manage objects in a given compartment. You can also have a specific rule where you can use the where clause to specify the bucket name. If you want your functions in the Acme function dynamic group to be able to read and write to all resources in a compartment, then you must enter a rule similar to the one given on the screen, which allows your dynamic group Acme function dynamic group to manage all resources in the compartment, and you must specify your compartment name or replace it with tenancy as per your use case. The third and the final step is to include a resource principal provider in the function code to enable the function to authenticate with other OCI services. First, let's discuss how authentication works with the resource principal provider. This provider uses a resource provider session token, also abbreviated as RPST, to authenticate functions with other OCI services. This token ensures that functions can securely access the necessary resources defined by their policies and dynamic groups. Next, consider access control. The RPST is only valid for resources that the dynamic group has been granted access to, making it a robust mechanism for enforcing access policies. This helps maintain strict control over what resources your functions can interact with. An important aspect to note is token caching. The RPST is cached for 15 minutes, which means any changes to policies or dynamic groups will take up to 15 minutes to be effective. This caching mechanism helps optimize performance while maintaining security. When it comes to implementation, we recommend using the resource principal provider included in the OCI SDK. This SDK streamlines the process, ensuring your functions can easily authenticate with OCI services. Alternatively, if you prefer not to use the SDK or are working in a language it doesn't support, you can write custom resource principal providers using environment variables and files within the function's execution environment. Let's go through the Python code example, which shows how to use the Oracle Resource Principal Provider to get a list of virtual cloud network from the Oracle Cloud Infrastructure. This statement import IO is basically importing a core Python library used here for handling IO operations. Import JSON, a core Python library again used for working with JSON data. From FDK import response, this line is part of the FN project's FDK for creating responses in serverless functions. And import OCI is to import the Oracle Cloud Infrastructure SDK used to interact with OCI services. Handler here is the main entry point for the function, called when the function is invoked. Here, CTX is the context object, provides information about the function invocation. The data object contains the input payload of the function invocation. Signer equals to this line gets a resource principal signer, which is used to authenticate the function with other OCI services using a resource provider session token, also known as RPST. The next line here calls the do function, which is defined later, with the signer as an argument and stores the response in the response variable. The next line, which is return response, this line returns the response from the function. It converts the response data to a JSON string and sets the content type header to application/JSON. Do signer is the function that performs the actual logic of listing the virtual cloud networks. Here the client line creates a new instance of the virtual network client class from the OCI SDK using the resource principal signer for authentication. The try block contains the code that may potentially raise an exception. This line calls the list_VCN method on the virtual network client instance to get a list of VCNs in the compartment associated with the signer. The signer.compartmentID provides the compartment OSID. The next line over here processes the list of VCNs returned by the list_VCN method. It creates a list of lists where each inner list contains the VCN ID and display name. If an exception occurs while listing the VCNs during the list underscore VCN call, it is caught here. If the exception is caught, the exception message is converted to a string and assigned to the VCNs variable. And this last line returns the list of VCN or the exception message in a dictionary with the key VCNs. In a nutshell, the handler function is the entry point to the function invocation, which gets a resource principal signer and calls the do function. The do function uses the OCI SDK's virtual network client to list the VCNs in the specified compartment and returns the list in a structured format. The response is returned as a JSON object with the list of VCNs or an error message. To wrap up, we have covered the integration of Oracle functions with various OCI services. We have also explored how to access other OCI resources from running functions such as VCN. By integrating OCI functions with these services, you can enhance the functionality and scalability of your functions, allowing you to build more comprehensive and efficient cloud applications. I hope you found this lesson interesting. See you in the next one. Thank you for watching. Hello and welcome to this demo on integrating OCI functions with other Oracle products. I am Mahindra Mehra, your senior OCI instructor with Oracle University. In this demo, we will cover how to use function to get a list of VCNs from the networking service in a given compartment. When a function you have deployed to OCI functions is running, it can access other Oracle Cloud Infrastructure resources. To enable a function to access other Oracle Cloud Infrastructure resource, you need to include the function in a dynamic group and then create a policy to grant the dynamic group access to that resource. We discussed the setup of dynamic groups and policies in the last lecture video, and in the interest of time, I have already set up the dynamic group and the required policies. Let's take a look at them now. I'll switch to the OCI console. Let's look at the dynamic group that I've created. To view the dynamic group, I'll click on the navigation menu, go to Identity and Security, click on Domains. I'll select the root compartment, click on Default Domain. Here I'll select the dynamic groups, and Acme function dynamic group is the one that I've created for this demonstration. And from the rule, it specifies that it is for all the functions. As you can see, the resource.type is set to FN function within the compartment as specified using the compartment OSIT. This is for my CTD OKE compartment. Well, this dynamic group is for all the functions in the CTD OKE compartment. Now, having created the dynamic group that includes the functions, we can now go and look at the policy that I have created for this dynamic group. So to view the policies, I'll click on the navigation menu, go to Identity and Security and click on Policies. I'll select the parent compartment where I've created the policy. Mahindra is the parent compartment for CTD OKE, and here I've created the dynamic group policy, which says allow dynamic group Acme function dynamic group to inspect VCNs in compartment CTD OKE. Well, this policy allows the dynamic group, which includes all the functions in CTD OKE compartment, to inspect VCNs in the same compartment, which is CTD OKE. Alright, now I'll move to the next tab where I have the Cloud Shell terminal open, and for this demo I have already set up the required files in the function-vcn directory, and these includes, ls, function.py file, function.yaml file, and requirements.txt file. Let's look at each of the file. I'll open up the function.py file. Well, this is the Python file and the Python code that will help us fetch the VCN details using the RPST token. Since I've already discussed this code in the previous video, I'll skip this for now. I'll press Ctrl X. Let's look at the function.yaml file. I'll open up the function.yaml file. Now let's break down function.yaml file. Well, the first entry is the schema version, which specifies the version of schema used in the file. Then we have the name. This is the name of the function, which in this case is OCI list VCN. We have the version entry, which specifies the version of the function, which is set to 0.0.2. Runtime here is set to Python, as we are using the Python code for this particular function. Then we have the build_image field, which is set to FN project Python, and the version used is 3.11. The run_image field is set to the container image used to run the function, which is Python 3.11. Next, we have the entry point command to run the function. Here we are specifying the path to the function handler. And lastly, we have the memory field, which specifies the amount of memory allocated to the function, which in this case is 256 MB. I'll close the file here. And let's look at the requirements.txt file. There are two values in the requirements.txt file. One is the FDK entry, that is the functions development kit for Python, enabling the functions to interact with the FN project. Another one is for the OCI SDK for Python with version 2.2.18 or higher. I'll close this file. Now let's quickly look at the current context that has been selected for FN project. I'll do an FN list context. And as you can see, the current context is pointing to US Aspen region, and the registry that is selected is hello world-java, which means when we deploy this function, the function image, the container image, will be stored under this repository path. Now before I deploy this function, we'll go to the OCIR service, and I'll show you that there is no image at present. And once we deploy the function, the image will be present in the hello world-java repository. Now I'll deploy the function using the fn deploy command to an existing application, which is hello world-app, which you're already aware of. And then we will invoke the function using fn invoke command. Here I've used the fnb deploy command and specified the name of our application using the --app flag, which is hello world-app. Well, as you can see, when we run the fn deploy command, it creates a temporary Docker file to create our container image for the function. And it uses the build image and run image as described in the function.yaml file. Well, from the output, we can derive that the deploy operation has completed successfully, and it has pushed the container image for this function under this repository path. As you can notice, it says hello world-java/OCI list VCN, and the image tag is 0.0.3. And also we can notice that it has successfully created the function OCI list VCN. Now firstly, I'll go to the container registry and we'll look at the image if it's there. I'll click on the developer services, click on container registry. I'll select the CTD OKE compartment. And as you can notice, we have this hello world-java/OCI list VCN repo that's created, and it has one image in it. So that image is OCI list VCN :0.0.3. That is the tag for our image. Now I'll move to the developer services and click on applications. And this is the application in which I've deployed the function, right? So I'll click on this. And within the functions section, we can see that there is an entry for OCI list VCN function. And it's created using the image that was pushed to the OCIR repository during the fn deploy operation. Now to invoke this function, I'll go back to the Cloud Shell terminal. I'll clear the screen here. The command is fn space invoke space the application's name, which is hello world-app, and name of the function. In our case, it's OCI-list-VCN. Now once we run this command, it will invoke our function OCI list VCN, which will in return get the list of VCNs present in the CTD OKE compartment. Now just to cross check, I'll go back to the previous tab and we'll go to the networking service. I'll click on VCN. And as you can notice, we have 4 VCNs currently active within the CTD OKE compartment. So let's see if we can retrieve the list of these 4 VCNs using the functions. I'll go ahead and hit enter. Alright, so the command had triggered the function and it has returned the list of VCNs in the CTD OKE compartment. As you can notice, we can see that functions_demo is one of the VCN. Other one is cloudbank-VCN. The third one is VCN-IGD. And the fourth one is OKE, a VCN that is created for OKE. So these are the VCNs that we could list using a running function in OCI. So this concludes the demonstration where we have successfully set up a function to access OCI resources. We deployed it and invoked it to retrieve a list of VCNs. I hope you liked this demonstration. I'll see you in the next one. Thank you for watching. Hello and welcome to this lesson on creating functions using pre-built functions. I am Mahendra Mehra, your senior OCI instructor with Oracle University. So let's get started. Pre-built functions provide a catalog of ready-to-use tasks or actions implemented using OCI functions. This means you don't have to write, build, package, or maintain any function code yourself. Functions leverage existing integrations between OCI functions and other OCI services such as Event Rules and Connector Hub, offering a seamless integration experience. By default, when you use OCI functions, it automatically creates a dynamic group and an IAM policy with the necessary policy statements to run the pre-built function. It's recommended to accept this default behavior to ensure smooth operation. However, if you prefer not to have OCI functions automatically create the dynamic group and policy, you can choose the option to not create them. We'll now take a look at some of the pre-built functions offerings available. Database secret rotation with wallet pre-built function in OCI functions enhances your database security by automating secret rotation through MTLS connections. This function simplifies the process of maintaining secure database credentials. Common use case scenarios include configuring the function to automatically rotate database secrets using a JDBC connection with a wallet, ensuring secure MTLS connection to the database. Alternatively, you can set up the function to rotate secrets using a JDBC connection without a wallet, providing flexibility based on your security requirements. By employing this function, you can ensure your database secrets are regularly updated, minimizing the risk of credential compromise and enhancing the overall security posture of your database systems. Next up, document generator pre-built function in OCI functions efficiently creates PDF documents from Office templates and JSON data. This function simplifies document creation by automating the process of combining template and data. Common use case scenarios include placing an Office template and corresponding JSON data in object storage, then directly invoking the function to generate the PDF documents. The generated PDFs are then stored back in object storage, streamlining your document management and reducing manual effort. This automation is particularly useful for generating reports, invoices, and other standardized documents. Next is Media Workflow Job Spawner function. This function triggers media workflow jobs automatically when video content is uploaded to an object storage bucket. This function is particularly useful in scenarios such as encoding a video file into different resolutions immediately after it is uploaded into a bucket, or encoding an audio file at various bit rates upon upload. By automating these processes, you can ensure that your media content is efficiently prepared and optimized for diverse use cases and platforms. Next is the Object Storage File Extractor pre-built function. This can be used to streamline your data management tasks. The function reads a zip file from an object storage bucket and extracts its content to a specified target bucket. Common usage scenarios include placing a zip file in an object storage and using OCI data integration to automatically unzip the file and store the results in the same or another bucket. Alternatively, you can place a zip file in object storage and directly invoke the function to perform the extraction and storage process seamlessly. This automation simplifies handling and processing large datasets, enhancing efficiency and workflow management. Next is the Object Storage FileZip pre-built function. This function is designed to zip files stored in an OCI object storage bucket and save the resulting zip file to a specified target bucket. It simplifies the process of compressing files within OCI, making it easier to manage and transfer large sets of data. There are two primary ways to utilize the Object Storage FileZip function. One is using the data integration workflow, where you place files in an object storage bucket and use the OCI data integration to automate the process of zipping these files and storing the resulting zip file back in object storage. Another way is to use direct invocation. You must place the files in an object storage bucket and directly invoke the Object Storage FileZip function to zip the files and save the resulting zip file in the target object storage bucket. Lastly, we have the Zero Quota Policy Creator function. This function enforces spending limits by creating quota policies that prevent the creation of OCI resources in specified compartments. This function helps in managing OCI spending and ensuring budget adherence. Common use case scenarios here includes preventing resource creation after a certified spending threshold is met. This is done in two steps. In step 1, we create a budget for a specific compartment and set up a budget alert rule to trigger based on actual or forecasted spending thresholds. This step ensures you are alerted when your spending approaches or exceeds the defined budget. Step 2 is to configure an event rule in the root compartment that triggers upon receiving the budget alert. This rule will invoke the function created from the Zero Quota Policy Creator, effectively applying a zero quota policy to the compartment, which prevents any further resource creation. By using this function, you can automatically enforce budget limits and prevent unexpected spending by restricting resource creation when a budget threshold is reached. In conclusion, pre-built functions offer a streamlined solution for executing common tasks or action within OCI functions. By leveraging a catalog of ready-to-use functions, users can quickly implement various functionalities without the need to write, build, or package, or even maintain custom function code. I hope you found this lesson useful. I'll see you in the next one. Thank you for watching. Hello and welcome to this lesson on function image security. I am Mahendra Mehra, your senior OCI instructor with Oracle University. In this lesson, we'll explore crucial aspects of securing function images deployed within OCI functions. Functions image security is paramount for ensuring the integrity and trustworthiness of deployed functions. So let's dive in and get started. Let's delve into the security options aimed at safeguarding our function images. Our first focus will be on scanning function images. This feature allows us to enable or disable scans of function images that are pushed to the container registry using OCI functions. Additionally, it enables us to check the scan results to identify any vulnerabilities detected in those function images. You can set up Oracle Cloud Infrastructure Registry, also known as Container Registry, to scan images in a repository for security vulnerabilities published in the publicly available Common Vulnerability and Exposure, also known as CVE database. To perform image scanning, Container Registry makes use of the OCI Vulnerability Scanning Service and Vulnerability Scanning REST API. When new vulnerabilities are added to the CVE database, the Container Registry initiates automatic rescanning of images in repositories that have scanning enabled. You can gain valuable insights into each image scan conducted over the past 13 months. This includes an overview of the number of vulnerabilities detected and an overall risk assessment for each scan. Additionally, you can delve into comprehensive details of each scan, featuring descriptions of individual vulnerabilities, their associated risk levels, and direct links to the CVE database for more comprehensive information. This historical and detailed data empowers you to monitor, compare, and enhance image security over time. You also have an option to disable image scanning on a particular repository just by removing the image scanner. Next on our agenda is signing function images. This crucial security measure involves digitally signing function images before deployment. By signing function images with master encryption keys, we can ensure their authenticity and integrity. This process adds an extra layer of protection, ensuring that only verified and unaltered images are deployed within our environment. Ensuring the unaltered integrity of software is paramount for compliance and security in a production environment. Let's delve into the mechanisms that guarantee this integrity within the context of OCI. Firstly, image signatures play a pivotal role in not only verifying the source of an image, but also ensuring its integrity. Oracle's Container Registry facilitates this process by allowing users or systems to push images and sign them using a master encryption key sourced from Oracle Cloud Infrastructure Vault. It's worth noting that an image can have multiple signatures, each associated with a distinct master encryption key. These signatures are uniquely tied to an image's OSID, providing granularity to the verification process. Furthermore, the process of image signing mandates the use of an RSA asymmetric key from OCI Vault, ensuring a robust and secure validation of the image's unaltered integrity. Finally, enforcing the use of signed images from the registry ensures that only verified sources are allowed when deploying in a function application. This process permits only signed images, enhancing the security and integrity of your applications. Let's dive into the steps you need to follow to ensure your functions are secure. Firstly, signed images play a pivotal role, providing a means to verify both the source and integrity of the image. You must obtain master encryption keys. These keys are crucial for signing the images that you will push and pull from the Oracle Cloud Infrastructure Registry. You can retrieve these keys from the Oracle Cloud Infrastructure Vault. Next, create an image signature verification policy. This policy will define which master encryption keys must be used to sign images when creating, updating, deploying, and invoking functions within your application. This step is vital for enforcing image security. When deploying functions using the fndeploy command, you need to specify the master encryption key in the function's YAML file. During deployment, the fn project CLI will sign the function image with the specified master encryption key, ensuring that only authenticated images are used. For creating and updating functions, always base your functions on container images that have been signed by the master encryption key specified in your policy. This practice ensures that every function you create or update is derived from a secure, verified image. And lastly, follow image signing process as outlined by OCI. This involves using the fn project CLI to sign your function images and adhering to OCI's guidelines for maintaining image security within the OCI registry. To wrap up, in this lesson we covered prioritizing security through active vulnerability management, ensuring unaltered integrity, and relying on trustworthy sources for robust container image security. I hope you found this lesson useful. I'll see you in the next one. Thank you for watching. Welcome to this lesson on OCI functions, logs, metrics, and tracing. I am Mahendra Mehra, your senior OCI instructor with Oracle University. In this session, we'll explore different options to effectively monitor and manage your functions to ensure optimal performance and reliability. So let's get started. Let's start by exploring the critical role of function logs in troubleshooting and monitoring the behavior of your functions. Our first stop is the Oracle Cloud Infrastructure Logging Service, our default and highly recommended option for accessing, searching, and storing function logs. It's your go-to platform for efficient log management. But wait, there's more. Also have the option to send function logs external logging destinations such as Papertrail. This feature offers flexibility and customization options to suit your specific logging needs. Additionally, you can configure the fn project CLI to specify a syslog URL for sending logs. And last but not least, a friendly reminder: for effective storage and viewing of function logs, it's crucial to include print statements in your function code. This ensures that your logs contain the necessary information for comprehensive analysis and troubleshooting. As you can see on the screen, there are different print statements that you can use as per the programming language of your choice for Node.js, for Java, and for Go. Now that we've covered the theory on OCI functions logs, let's move on to a practical demonstration to see how we can store and view these logs in the OCI console. I have already logged into my OCI console, and now I'll open the navigation menu and click on Developer Services. Here under Functions, I'll click on Applications. You must ensure that you have selected the region and the compartment that contains the application with the functions for which you want to create, enable, and view the logs. In my case, I have just one application listed. I'll go ahead and click on the application name Hello World-app. Now under the resources section, I'll click on logs. As you can notice, currently the function invocation logs are disabled. We can click on the action menu here and click on enable log. This opens up the enable log window. Here we must specify the compartment where we want to create the new logs, and by default it is the current compartment, which is ctd-oke. Next is the log group in which to create the new log. We can select an existing log group or use the default group. For this demonstration, I'll use the group with the name default group. Under log name field, we must specify the name of the new log. By default, it is set to the application name _ invoke. If you wish, you can change it. In my case, let's say I say invoke _1. And under log retention, you specify the length of time to retain your log data. By default, it is 1 month and I'll leave it to the default value. I'll go ahead and click on enable log. With this, we have enabled the function invocation logs for our application. Now that I have enabled the logs for our function in the application hello world-app, let's go ahead and invoke the function a couple of times. I'll simply run the commands to invoke the function. One is the hello world Java existing function, and the other one is the hello-java function. Let's do it a couple of times to generate more data. Well, I've invoked the functions hello world Java existing and hello-java 2 times each. Let's go back to the first tab, and to view the logs, I'll click on the log name. Now in the explore log window, we can notice the different logs that are available, like the invocation logs that are available for the request that we sent to the functions. Now here what we can see is it recorded the invocation request service time, like it served the function invocation request in 4.117 seconds. For one of the requests it was 0.043 seconds, and one of the requests it was 0.159 seconds, right? So here you can notice all the logs for the function invocation that happened. And if you wish to see the log in more detail, you can click on the drop down here, and this gives you more detailed information in JSON format. You can also sort the log entries based on newest and oldest values, and you can also filter by time. Let's say if you want to view logs for the past 3 hours, you can select the value past 3 hours, or you can also select a custom value where you specify the date range within which you wish to view the log details. And if you want to search through the log data, you can use the explore with log search option that is available. This feature helps you narrow down your search using custom filters. And that's it. With this, we've come to the end of this demo where you successfully learned how to enable and view function logs in OCI logging service. Now that we've wrapped up our hands-on demonstration of OCI function logs, let's transition back to our slides to delve into the next topic, which is function metrics. Given the length of this video, I'll pause here and we'll pick up where we left off in our next session. I hope you're finding this content engaging and insightful. See you in the next lesson. Welcome back. Let's continue from where we left off in our previous lesson. Let's discuss the realm of OCI functions metrics, where insights into the health, capacity, and performance of your deployed functions await. With metrics emitted in the OCI_FAAS namespace, you gain visibility into crucial aspects such as functions invocations, execution duration, error responses, and throttled invocations. These metrics provide a comprehensive overview of your function's behavior and performance. In addition to monitoring function execution, OCI functions also facilitates monitoring of memory usage and availability. This feature ensures efficient resource management and optimization of function performance. Keep in mind that default service metrics are updated at a frequency of 60 seconds, ensuring that you have timely and accurate data for analysis and decision making. To monitor resources, you must be granted the read access to the metrics in the compartment. You can specify the policy statement such as allow group to read metrics in compartment, and this will give your users access to the metrics emitted by OCI functions. Let's move on to a hands-on demo to see how we can monitor these metrics directly in the OCI console. In this demo, we'll explore how to access and interpret function metrics to gain insights into the health, capacity, and performance of our deployed function. Let's switch over to OCI console to begin the demo. I'm already logged into my OCI console and this is my OCI dashboard. To view the default metric charts for a single function, we must click on the navigation menu, go to the developer service, click on applications. Ensure that we have chosen the right compartment and the region where our function is created. Now I'll click on the name of the application containing the function for which we want to view the metrics. I'll click on hello world-app. Within the functions section, we have two functions listed. I'll select the hello Java functions and we will be viewing the metrics for this function. Now the metrics page displays a chart for each metric that is emitted by the metric namespace for OCI functions. The first metric that it displays is the invocations, that is the total number of functions invocation. The next chart is the duration chart, which specifies the total duration the function executed. The next chart is for the errors, which specifies total number of function invocation errors. And since there was no invocation error, so no data is available for the time range. And the next chart is for throttles, which indicates total number of throttled function invocations. Again, since there was no throttling operation that happened for this function, we have no data for this time range. Now the metrics that we are currently viewing is for the particular function within the application, right? Now if you want to view the metrics for all the functions within the application, we must go to the applications page. Currently I'm on the applications page and here under the resources section, I'll click on metrics. These charts over here displays the data for all the functions that are running within this application. From the output, you can notice we have the data for both the functions, that is hello-java and hello world-java-existing function. And here is the function duration that for which these functions ran, including the function's error chart and the function throttle chart for both the functions. And of course, it has no data for the time range as there were no errors while invoking the functions and no throttling was really required while running the functions. And let's say you want to view default metric charts for all the functions in all the applications within your compartment. Then in that case, we'll go to the observability and management section. And here under monitoring, we'll click on service metrics. Ensure to choose the right compartment. In our case, it's CTD-OKE, and you choose the right region. That is where your functions are hosted. Under the metric namespace, select OCI_FAAS, which is function as a service metric namespace. And this basically displays the charts for all the functions and all the applications that are running within the CTD-OKE compartment. Make a note that the service metrics page will dynamically update the page to show all the charts for each metric that is emitted by the OCI_FAAS metric namespace. With this, we come to the end of this demo where we saw how to view metrics for all the functions in an application using various charts like function invocations, function duration, function errors, and function throttles. Let's return to our slides to continue with the next topic, which is distributed tracing for functions. In this segment, we'll explore how distributed tracing helps us debug function execution issues and understand the performance of our serverless applications. Enabling tracing for OCI functions is crucial for debugging and performance analysis. By enabling tracing, we gain insights into how functions move through various components of the system. This helps us identify and troubleshoot issues effectively. The integration with the OCI Application Performance Monitoring Service enhances our tracing capabilities. Distributed tracing is particularly beneficial in various scenarios. For instance, when one function calls another function, or when functions interact with external services such as object storage or serve as a backend for API gateway. Additionally, tracing helps us understand how functions respond to events triggered by the event service, notification service, or connector hub. OCI functions tracing capabilities are powered by the OCI Application Performance Monitoring Service. APM offers a range of features to identify and troubleshoot failures and latency issues in the functions we create and deploy. With APM, we can gain valuable insights into the performance of our serverless applications and ensure optimal execution. To wrap up, in this lesson we delved into the essential practices of observing functions within OCI functions. From logging and tracing to monitoring metrics and limits, we've explored the tools and techniques necessary for gaining insights into functions' behavior and performance. By leveraging these capabilities, you can ensure the reliability, efficiency, and optimal functioning of your serverless applications in Oracle Cloud Infrastructure. I hope you found this lesson useful. I'll see you in the next one. Thank you for watching.
Welcome to this course on API management. This is a level 100 course. My name is Robert Wunderlich. I'm a product manager with Oracle Cloud Infrastructure. In this course, we will discuss APIs and API Gateway. We will walk through the steps to prepare a tenancy for API Gateway, and we'll create some APIs. We will explore how we can use API Gateway to create a protected HTTPS endpoint for APIs, and how the gateway can apply policies that validate API requests, enforce authorization, work with runtime context, and transform API requests between our clients and our backend implementations. We will finish up with monitoring and managing APIs through logging and metrics. Let's get started. So what is an API and API Gateway? The term API, or Application Programming Interface, has been around for a very long time. Developers use them in many of the popular programming languages such as Java. Rather than implement everything from scratch, developers make use of libraries to accelerate their development simply by importing the libraries that they need. The developer interacts with the pre-built capabilities via a well-defined API. We can refer to this as a local execution because the developer imports the necessary libraries into her project, but it is encapsulated as the developer does not need to deal with the internal implementation of the API. Web services share the fundamental principles of encapsulating the implementation, but have some distinct differences. Like their name indicates, they are typically available over the web. They are highly decoupled, meaning that a client application invokes the web service over the wire, and the code for the web service does not typically run in the same context as the application that is using it. As a matter of fact, the web service is often written in a wholly different language than the client that is using it. As we've come to refer to web services as APIs, throughout this course, whenever we say API, we are talking about web services. So as we were talking about, what is the API? We have clients, and those clients need to use functionality on a server. So they connect to the server over the wire or the web service, which is a well-defined contract that we'll talk about in a moment. We need to be able to protect that endpoint because if that web service is available to the World Wide Web, anybody, not just the client we intend, could try to get to it. So we use an API gateway, and that API gateway provides an interface for the clients to be able to use and connects to the backend web services. So the client is not aware of the implementation of the backend web service. The client just interacts with the API gateway. So let's delve into the elements of an API. An API comprises a description, a set of policies, and an implementation. So beginning with the description. The description is a contract between the consumer and the provider. It describes the functionality of the API. And there's a wide range of tools available for creating API descriptions. You can use Postman, Stoplight, Swagger Editor, Code Editor, and many more. Description is typically written in a format such as OpenAPI, which is an implementation agnostic way to describe the behavior, and it's well recognized in the industry. When our API is being made available, that endpoint needs to be protected. And so we use the API gateway. The API gateway applies policies to enforce protection, such as authorization. It also performs validation, transformation, and routing. Another benefit of using an API gateway is it can add metrics, alarms, and logging for that endpoint. When implementing the actual functionality of the API, the choices are endless. You can implement on Oracle Kubernetes Engine, you can use Helidon, you could have custom code running in Compute, you could create modern serverless APIs using Oracle Functions, you could work against the Autonomous Database and Oracle REST Data Services, you could work against a wide range of SaaS applications, you can connect to just about anything with integration, or you can use any other technology. So the API gateway is a network-attached device, and it connects between the client and the backend servers. So the clients from the outside connect through the gateway to the backend services. And of course, those services can be running in OCI or through OCI connected to your data center. The API gateway provides security, mediation, and monitoring. So the Oracle Cloud Infrastructure API gateway is a serverless policy enforcement point. It adds authorization, rate limiting, and routing. It performs request validation. It also performs request and response transformation. To help ease the load on your backend services, it includes response caching. You can create both public and private endpoints. So you can have internal APIs running that are not accessible to the internet, and you can also have public APIs. You can also set up custom domains so that you can have APIs under your own host names. The gateway also includes integrated logging and metrics, and you can also use advanced logging analytics with API Gateway. As you're designing your APIs in Open API 2 and 3, you can load those into the gateway, and you can quickly create API deployments that have built-in mock testing. As you deploy your APIs and make those available for developers to create applications and use them, you can generate SDKs so the developers can work with your APIs in the language of their choice. Let's set up our tenancy for using API Gateway. API Gateway is a network-attached device. So if we do not yet have a virtual network, we need to first create one. The Virtual Cloud Network, or VCN, contains multiple resources. For example, subnets. Our subnets can be both public and private. API Gateway appears as a network device on the subnet of your choosing. API Gateway is fully managed by Oracle, and it has built-in failover capabilities. Therefore, when creating a gateway, you will always use a regional subnet. When you create a gateway, the API Gateway service automatically provisions your gateway with an active and failover instance. In a region with multiple availability domains, the instances are created in separate availability domains. If there is ever an interruption to the service in the availability domain the active instance is running in, the service will automatically fail over to the backup domain. In the case of a single AD region, the gateway will be provisioned across 2 fault domains. All of this is transparent to the user. As you set up your network, you will need to ensure that the traffic can ingress into and egress from the gateway. Oracle Cloud Infrastructure is secure by design and follows the principle of least privilege. This means that the appropriate ingress rules need to be added to the security list, and depending on your chosen network topology, you may need to add appropriate routes to your route tables. Continuing the principle of least privilege, access is never assumed, and policies have to be added to explicitly allow access. It is best practice to set up a well-defined groups in OCI identity management and then add the appropriate policies for the access needed. Users are not directly granted access to resources. Rather, policies are created to grant access to groups, and users are then added to those groups. When a new user is created, that user has no resource access until that user is assigned to a group. When enabling your teams to develop APIs, they will need to be granted the appropriate permissions through group membership. Resource-to-resource access is also controlled through policies. For example, if you want to create a serverless API with API Gateway and functions, you must add a policy to allow API Gateway to invoke the functions. Here we are in the OCI console. As we talked about before, we need to set up the network and also security policies before we use our first API Gateway. Okay, so the first thing we want to do is go ahead and create a network. So I'll go ahead and go into networking, and I will select Virtual Cloud Networks. Super important is to make sure that you have the appropriate compartment. Here I have L100 development checked, and that's what I want. So I'm going to go ahead and create a virtual cloud network. Now what I can do is I can create a VCN, or I can start the VCN wizard. So here I'll give my VCN a name. Again, I'm ensuring that I am in the appropriate development compartment, L100 development. My CIDR blocks are automatically filled out for me. I'll go ahead and leave those as is. And everything looks good, so I'm going to go ahead and create my VCN. The wizard will go through and create all of the necessary resources for my VCN. It's fairly quick. Okay, so my new VCN is created. Let's go ahead and view it. In my VCN, I have a number of resources. I have a private subnet and a public subnet. API Gateway can work on either private or public subnets for different use cases. I also have a number of other resources created, such as my NAT gateway, my service gateway, the HTTP options, my security list. As a matter of fact, security lists are super important, and this is something that will trip a new user up for API Gateway. The example is I go and create my VCN, and then I'll ultimately create my gateway, create an API, and I'll want to test it. And as I go to invoke it from my test client, from the internet, I will be confused in that I won't be able to get a response. My gateway will appear to me that it is not working. And what it is the security list has not been properly configured. So in this case, what I'm going to do is I'm going to go to my default security list for the L100 API management VCN, and I'm going to add an ingress rule. You notice here there's a default ingress rule of port 22, which is SSH. And that's all you get when you set up a network. OCI is secure by design. So there's no assumptions made as to what type of resources you're going to run. And all of your security lists are totally locked down, and you have to actively open up the appropriate ports. So I'm going to add an ingress rule. So what I'm going to do is I'm going to say 0.0.0.0/0, essentially everything from the internet. The IP protocol is TCP, and I'm just going to say 443. API Gateway only allows HTTPS traffic in at this point. So what I'll say is HTTPS traffic for API Gateway. This is an optional description, but just as I go back and I'm looking at this at a later point, and if I'm wondering why I have that open, I have a description telling me why. So super important step. Like I said, a lot of people, what happens is they get into trying things out, spin up the gateway, wondering why they can't connect to it. Simple thing, we just need to go ahead and allow, open the gate, so to speak, to allow that traffic to come into API Gateway. So as far as networking is concerned, we're all set. Let's go ahead and create some policies. So I'm going to go to Identity and Security, and I'm going to select Policies. Here I'll create a policy. I'll give my policy a name. Allow API Gateway, call functions. This is in my development compartment. I'm going to go ahead and select the manual editor. This is a little more complex policy, but once we go through it, it'll make sense. So I have this already copied just for time, and I'll go ahead and paste this in. All right, so what does this tell us? We're going to allow any user to use functions family in the compartment development where and these are conditions. All, the request principal type is API gateway, and the request resource compartment ID is this compartment ID. This is my development compartment ID. My gateway will happen to be in the same compartment as my functions, but I could have those in separate. So I could have a policy that is defining for functions in a separate compartment altogether. Different users are working on those, and I need to allow the gateway to be able to invoke those functions at runtime. This is for creating serverless APIs, and so we want to give API gateway the resource principal access to be able to invoke functions. So that policy is created. I could add a few more policies, and I'm going to go into another compartment just to show those examples. So if I look in this compartment, I have a set of policies for my API developers. I've set up a number of groups. I have API developers, API managers, gateway managers, and so forth. So my API developers can manage the API gateway. They can manage the network, the functions, everything within the development compartment, rather. They can work. They're free to do what they need to do to build their APIs. Just for context, a little bit of an example, let's go ahead and take a look at the QA compartment. So here I have access control for developers and testers for QA, UAT. When I take a look at this, I can see that I have a group API testers, and they can manage the API gateway in the QA compartment. Functions family, they can work with that. And if we look down the line, we can see developers can view those resources, but they can't change the resources. And that's as the API progresses through the development lifecycle. We do not want developers making changes directly in QA. We would want to limit that. So we have a testers group. And this is how we give rights to users to be able to work at development time and configuration time. We add those users to groups. So we assign the rights to the groups, and then we go ahead and create the appropriate policies to allow the appropriate access. But again, at runtime, that policy I created for the gateway is a dynamic policy of sorts, because any gateway I create in that compartment would have access. So I can add and change and take away gateways. I don't have to add each one into a specific group to solve that. So that covers what we need for networking and also policy. Let's go ahead and go create a gateway. So I'm going to go back to my menu. I'm going to select Developer Services. And under API Management, I'm going to select Gateways. I'm going to ensure that I'm in the correct compartment. So I'm going to select L100 in Development. And I'll go ahead and create a gateway. Give my gateway a name. This one I'll make a public gateway. You can make a public or a private gateway. And this one I'll make public because I want to have a publicly accessible address so I can create APIs and test against it. It's in the correct compartment, L100 Development. I'm going to go ahead and select my VCN that I created, which is my L100 API Management. And you notice we have regional subnets here, private and public. I'm going to go ahead and select public. Then I'll go ahead and create my gateway. Okay, my gateway has now been created, and I'm ready to go to start creating APIs and deploying them. In this module, we're going to create an API. We're going to begin with an API description, and we'll load that into API Gateway, and then we'll use that description to create a mock deployment. But before we do that, let's go ahead and talk about what this entails. A key element of creating an API is to be able to prototype that API. So we can create a description of the API. Ultimately, we're going to implement that API by creating a web service. However, that web service may not immediately be available after we've designed our API. Oftentimes, a team has to come and implement that web service on the back end in parallel with the team that's using the API on the front end. So what we can do is use the API Gateway. By loading our description into API Gateway, we can very quickly create a stock response deployment in API Gateway. API Gateway will serve the API. It will return the example response for clients invoking that API. This is also useful to be able to test that API to validate that it is meeting the requirements for the project. Once the backend web service is implemented, then that can be connected in API Gateway to serve the ultimate request. So to create and prototype an API, you create an open API description, and you can use any tool that you wish. You can load this into your API Gateway. Then you can deploy the API, and API Gateway will automatically define it as a stock response and use your example in your open API description. Then you can test it out with your client. Let's go into API Gateway. We'll build an API description, load it into API Gateway, deploy it as a stock response, and test it out. Here we are in the OCI console. We'll navigate over to API Gateway under Developer Services, API Management, and we'll choose APIs. APIs represent a repository of API descriptions. I'm going to go into an existing compartment, and we can see some of that we already have loaded. We can support both OpenAPI 2.0 and OpenAPI 3.0 definitions. So this is an example of one such definition that we have loaded. What I'm going to do is go ahead and work on one of these APIs or show how we might be able to edit one of these APIs. Very simple. There's many tools on the market. One such tool is Swagger Editor. I've pulled this up in my web browser, and I have an API definition. What you can see here is this is a field service API. It's a sample ticketing system. So in this API, we have a definition of services, such as to get tickets. It includes information about the required parameters for the service. It also includes some example data that can be used for generating samples. So what we're going to do is we're going to deploy this or load this into API Gateway. So within API Gateway, I'm going to choose my compartment that I want to work with. And I'll work with my L100 compartment. I'll go to my development compartment. So what I'm going to do is I'm going to go ahead and create an API. And I'll call this field service. And then what I'm going to do is I'm going to choose my file. So here's a copy of my API description. This was written with a file name of swagger.yaml. Swagger is old name that we used to call OpenAPI definitions. There's still Swagger tools that we work with, and that's what Swagger now stands for today as Swagger tools. OpenAPI is the new term. So if it's OpenAPI 2.0, that's what was formerly called Swagger. And if it's OpenAPI 3.0, that's the next format of OpenAPI. API Gateway does support both. In this particular file, I have OpenAPI 2.0. So I've loaded this into API Gateway, and a couple things are happening. One is the API Gateway is validating the file that I've loaded to make sure that it is semantically correct. And then what it will do is it will create a predefined deployment object that can be used to quickly create API definitions for this API. So it's validated, and now the deployment specification is generated. So I'll go ahead and deploy this to a gateway. So I can choose deploy, and I can go ahead and choose my gateway. And this is my L100 training gateway that I created, so I'll use that. I'll call this field service. And I'll give this a path prefix. So I'll just call this FSV1. I can call it whatever I want. Now, what I have here is a number of policies. So we'll get into detail with the different policies that we're going to be using. But what I'm going to do is I'm going to go ahead and add one necessary rule for a test client that I'm going to use in a moment. And I'll explain that shortly. So what I'm going to do is I'm going to go ahead and say I want to allow all origins. I want to allow all methods. And I'm going to allow loud header of x-api-key. This is a header that is included with that API definition, so I'm including that. This is to make a test client work that I'm going to use. There's many different test clients, many different ways, and I'll explain that as we go through. I'm going to go ahead and apply that change. I'm going to go to my next screen. What we can see here is there's a stock response that's automatically pre-populated for us. This was the example that was within that definition. So when I load this into API Gateway, it automatically creates or pre-populates my route for me. This is the method that I had defined, which is just a get. And of course, this is a stock response. This can go against Oracle functions, or it can also go against HTTP backends. So I'm going to go ahead and create my API. This will take roughly about 30 seconds on average, 30 seconds or less to go ahead and create the deployment, and then we'll go ahead and test it. So in this case, what I'm going to do is I'm going to copy the deployment, and I'm going to go into my test client while it's deploying. So I can come back here to Swagger Editor. There's two elements here that I've left not populated, and I'll go ahead and start populating these. So I'm just going to paste the endpoint that I have and go ahead and make some changes. So here we have the host value, and then we have the base path value, which I'll go ahead and take these, and I'll put these in place in my file, and I'll go ahead and uncomment these. Take out the to-do, and I'll also take out the to-do here at the base path. Okay, so I have this created. This is set, and so what I can see here is in Swagger Editor, I have my code or my Swagger file, which is written in YAML. It could also be written in JSON. And then I have on my right-hand side dynamically generated documentation. That includes a tester. So what I can do is go ahead and select this, and I'm just going to give this a API key. I'm not doing anything with the API key right now. I'm just using it to satisfy the request. So what we see here is I've made the request. So it's called the service, and I've gotten a response. Now there's no backend service implemented. It's just within the gateway, and the gateway is returning a response. So what I can do is work with my team, and I can work with my front-end developers and my back-end developers, and we can make sure that this API definition is doing what we want. And as long as we're all comfortable with what's happening and the kind of the behavior, then what we can do is send the front-end developer teams off to go build the front-end apps. The back-end developer teams can work on the back-end developer apps, and then they can go ahead and tie the API gateway to the actual back-end when they implement it. Just for an example, I'm going to go ahead and copy the syntax here, and we'll go ahead and open up a terminal window. And if I were to paste this, what we should see, of course, is a return. Make this a little bit nicer. Let me see if I can get this as well. I'll just go ahead and paste this. There you go. So I get that nice formatted that we can see here, the response. So this is a live service. We can go ahead and call this, start writing front-end applications and work against the API. Now, this is one tool that I've shown, Swagger Editor. You can use multiple tools. So like, for example, we can go in the stoplight. We have this service here that we're working within. It's the same thing. All we're doing is just taking the file, the Swagger file or the Open API definition, and we're just loading it into our OCI API gateway. Another example just to call out real quick to kind of show how open everything is and how you can use different tools is we can go ahead and take this endpoint here, and we could go over to another popular tool called Postman. So here I'm in Postman. And so what I can go ahead and do is create a new request. I can go ahead and call the request here. Now, what you'll notice is I'm not really doing anything with that API key. I'm not validating that API key yet. This is just a stock response that's giving me that response. So with this, I've created an API description. I have loaded that API description, the API gateway, and I've gone ahead and created a deployment of my stock response and tested it within my test clients. And so that's the demo.
Hello, I'm Orlando Gentile, and in this course I will show you how Infrastructure as Code can be used with OCI. First of all, what is Infrastructure as Code? Infrastructure as Code is a practice that involves managing and provisioning computing infrastructure through machine-readable configuration files rather than through interactive configuration tools. Automating infrastructure management enhances efficiency by reducing manual tasks and optimizing resource utilization. Consistency refers to maintaining uniformity and stability in process, configurations, or actions, ensuring reliability and predictability across operations. Scalability refers to the ability of a system or application to handle increasingly workloads and adapt to change demands without compromising performance or reliability. Our first objective is to understand the basics of Terraform. We will start by exploring what Terraform is, why it's important, and how it fits in the world of Infrastructure as Code. We will cover the core concepts of Terraform, including providers, resources, and state, how to write basic Terraform configuration files, and a typical Terraform workflow: init, plan, apply, and destroy. The second objective is to dive deeper into using Terraform specifically with Oracle Cloud Infrastructure. Here we will learn how to configure Terraform to interact with OCI, explore the various OCI resources that can be managed with Terraform, such as compute instances, networking components, and storage, implement real-world examples, and use cases to solidify your understanding. Our final objective focuses on OCI Resource Manager, which is Oracle's managed service for Terraform. We will understand the benefits of using OCI Resource Manager, learn how to create and manage stacks using OCI Resource Manager, and explore advanced features such as drift detection and automation workflows. By the end of this course, you will have solid understanding of Terraform basics, know how to use Terraform with OCI, and be proficient in leveraging OCI Resource Manager to manage your infrastructure. Let's get started and dive into the world of Terraform and OCI. In this lesson, we will explore the fundamental concepts of Terraform, a powerful infrastructure as code tool by HashiCorp. Terraform is one of the most popular and versatile tools in the infrastructure as code arena. Let's look at some of its benefits that led it to this position. Terraform automates the provisioning, updating, and destruction of infrastructure resources, reducing manual effort and human error. It ensures consistent infrastructure configurations across development, testing, and production environments, promoting reliability and stability. Terraform supports scaling infrastructure resources up or down based on demand, making it suitable for dynamic workloads. Infrastructure code written in Terraform can be stored in version control systems like Git, enabling versioning, collaboration, and change tracking. Terraform works with various cloud providers and on-premises environments, allowing for a unified approach to infrastructure management. It supports modularization through reusable Terraform modules, making it easier to manage complex infrastructure configurations. Terraform provides a clear audit trail of infrastructure changes, enhancing transparency and compliance efforts. After looking at its benefits, let's shift gears and start working on Terraform essential concepts. First, Terraform commands. These are the instructions we give to Terraform to perform various actions on our infrastructure. We'll cover commands like Terraform init, Terraform plan, Terraform apply, and Terraform destroy. Next, providers. Providers are plugins that allow Terraform to interact with cloud providers and other APIs. They define the resources and the data sources that we can use. Resources are the core components of our infrastructure, representing services like virtual machines, databases, and more. We'll look at how to define and configure these resources. Variables help make our configurations more flexible and reusable. They allow us to parameterize our configuration files, making it easier to adjust settings without modifying the core code. Outputs provide a way to extract and display information from your Terraform configurations. They are useful for sharing data between different parts of your infrastructure or simply summarizing the state. Modules group related resources together into reusable packages, promoting code reuse and organization. We will see how to create and use modules to streamline our configurations. Finally, state. It is how Terraform tracks the current status of our infrastructure. The state file is crucial for managing changes and ensuring consistency across deployments. By understanding these Terraform concepts, you will be well equipped to manage and automate your infrastructure effectively. Stay tuned as we dive deeper into each topic. As those concepts are key for understanding Terraform, they will be individually presented with more details. Thanks for watching, and see you in the next lesson. Hello and welcome. In this lesson, we will cover the Terraform commands. The Terraform command line interface is a tool used to interact with Terraform, facilitating the creation, management, and deployment of infrastructure resources as code. The CLI is essential for executing Terraform workflows efficiently and automating infrastructure management tasks. Next, I will list some of the commands we will use in this course, but bear in mind that the list is longer. First, we have the version command. This command simply shows the current version of Terraform you are using. It's helpful to ensure you are running the expected version, especially when working in team environments. Next is init. This command prepares your working directory for other commands. It initializes the backend configuration and downloads the required provider and modules. Think of it as setting up your workspace for Terraform operations. Then we have validate. This command checks whether your Terraform configuration files are syntactically valid and internally consistent. It's an essential step before planning or applying change to catch any errors early. Moving on to plan. The plan command shows the changes required by the current configuration. It generates an execution plan, allowing you to review what will happen when you apply the configuration. This step helps you ensure that the changes align with your expectations. Next is apply. This command executes the actions proposed in the execution plan generated by Terraform plan. It creates, updates, or deletes resources to match the configuration. Apply is where your planned infrastructure changes are realized. After that, we have destroy. This command is used to delete all the resources defined in your Terraform configuration. It's useful for tearing down infrastructure that is no longer needed, ensuring a clean and controlled removal of resources. Then there's output. This command is used to extract and display the output values defined in your root module. Outputs are useful for sharing data between different Terraform configurations or simply summarizing the state of your infrastructure. Finally, we have FMT. This command reformats your configuration files to the standard Terraform style. It helps maintain consistency and readability in your code, making it easier to collaborate with others. By mastering these Terraform commands, you will be well equipped to manage your infrastructure efficiently and effectively. Thank you for watching, and see you in the next lesson. Hello and welcome. In this lesson, we will cover Terraform variables. Variables in Terraform allow us to make our configurations more dynamic and reusable. They enable us to parameterize our configurations, making it easier to manage and modify our infrastructure setups. Let's look at an example of how variables are used in Terraform. Here we define a variable named compartment_id. This variable has a description, type, default value, and validation rules. The description helps in understanding the purpose of the variable. In this case, it describes that the variable is the OCI compartment OCID. The type is set to string, meaning this variable will hold string values. The default value, default_compartment_id. This value will be used if no other value is provided. We have a validation block that checks if the length of the compartment_id is greater than 0. If not, it returns an error message saying compartment ID must be provided. This ensures that the variable is always set with a valid value. Next, we define another variable called availability_domain. This variable only has a description stating it is for the OCI availability domain name. On the right side, we see a resource block for an OCI instance named example_instance. Here's how we use our defined variables within this resource. We reference the availability_domain variable using var.availability_domain. This allows us to dynamically set the availability domain for our instance based on the variable's value. Similarly, we use var.compartment_id to set the compartment ID for the instance. This ensures that our instance is created in the specified compartment. Using variables, we make our Terraform configurations more flexible and maintainable. We can easily change the values of these variables without modifying the resource definitions, which simplifies the management of our infrastructure. A terraform.tf_vars file is used to set the values of variables in your Terraform configuration. This file allows you to separate configuration data from your infrastructure code, making your setup more flexible and easier to manage. On the left side of the slide, we have an example of a terraform.tf_vars file. Here we define values for compartment_id and availability domain. On the right side, we see a resource block on the OCI instance named example instance. Here's how the variables defined in the terraform.tf_vars files are used within this resource. The compartment ID variable is referenced using var.compartment_id, and it takes the value defined in the file. The availability domain variable is similarly referenced using var.availability_domain. Using terraform.tf_vars files helps in maintaining clean and manageable Terraform configurations, enabling you to efficiently handle different deployment scenarios. Understanding and using variables effectively can greatly enhance the scalability and adaptability of your Terraform configuration. Stay tuned as we continue to explore more Terraform concepts in our upcoming lessons. Thanks for watching and see you in the next lesson. A Terraform provider is a plugin that enables Terraform to interact with a specific cloud infrastructure platform such as OCI or services like Docker or on-premises infrastructure. Providers in Terraform are essential components that facilitate the interaction between Terraform configurations and specific Terraform platforms or services. Providers are plugins that serve as a bridge between Terraform and the target platform, allowing Terraform to manage resources, configurations, and deployments on that platform. Each provider implements its sets of resources, data sources, and functionalities specific to that platform. There are three types of providers: cloud providers, These providers interact with cloud platforms like AWS, Google, and Oracle Cloud Infrastructure. They allow Terraform to create and manage virtual machines, networking components, storage resources, and other cloud resources. On-premises providers. Terraform allows support on on-premises infrastructure management through providers like VMware, OpenStack, and Docker. These providers enable the automation of physical and virtual infrastructure within private data centers. Specialized providers. In addition to cloud and on-premises providers, Terraform has specialized providers for managing services such as DNS, databases like MySQL and PostgreSQL, content delivery networks, CDNs, monitoring tools like Prometheus, and more. Understanding providers is key to leveraging Terraform's full potential. By using providers, you can manage a diverse set of infrastructure components from a single configuration file. Now, let's take a look how to configure providers in Terraform. At the top, we have the required providers block. This block specifies a variable name for the provider and sets its value to provider identifier. In this example, we have a variable named OCI for the Oracle Cloud Infrastructure provider. The source is set to Oracle/OCI, indicating provider's official source. The provider identifier serves for two main purposes. Source location. It tells Terraform where to fetch the provider plugin from, whether it's Terraform registry, a private registry, or another source. Version control. Combined with the version attribute, it ensures that Terraform uses the correct version of the provider, which helps maintain compatibility and stability across your configurations. Below that, we have the provider block. This block includes the authentication details and settings needed to connect to the provider. For the OCI provider, we need to specify the tenancy_OCID, user_OCID, fingerprint, and the private key path, along with the region. You can use these values directly or reference values on a terraform.tfvars file, for example. These values are used to authenticate and configure the provider, ensuring Terraform can manage resources in the specified environment. Here is another example of a provider configuration on OCI. The required provider block is the same as the previous example, but on the provider block it's using a different type of authentication, token-based in this case, and different parameters are provided. By specifying the provider identifier correctly, you ensure that Terraform can locate and use the appropriate provider plugin to manage your infrastructure resources. This identifier is essential for linking your configuration to the actual provider code that interacts with your cloud or on-premises services. Thanks for watching and see you in the next lesson. Hello and welcome. In this lesson, we will look into the Terraform resources concept. In Terraform, resources encompass a broad range of infrastructure components essential for building and managing modern IT infrastructures. These resources are the building blocks that Terraform interacts with and provisions based on your configuration. They can be categorized in several types, each serving distinct purposes within your infrastructure. Let's break down the components of a resource block. The resource type identifies the kind of resource you are creating. In our example, OCI Core Instance specifies that we are creating an Oracle Cloud Infrastructure Compute instance. Several essential resources like compute, network, storage are grouped under the Core group. This is important to remember when navigating the resources documentation. The resource name is a unique identifier within the configuration for that resource. Here it's named example_instance. Inside the resource block, you define the configurations and attributes for the resource. These configurations specify the settings and properties for the resource. Attributes are key-valued pairs that define the properties of the resource. There are required and optional attributes according to the resource's type. Here we see the attributes and their respective values. In addition to standard attributes, you can also include metadata for additional configuration. For example, the metadata block can include SSH keys for the instance access. To learn more about different resources and their attributes, you can visit the Terraform registry. By defining resources in Terraform, you can manage and automate your infrastructure efficiently. Each resource block is a declarative way to specify the desired state of your infrastructure components. Thanks for watching, and see you in the next lesson. Hello and welcome. In this lesson, we will look at the Terraform output concept. In Terraform, outputs provide a mechanism for extracting and displaying information from deployed resources after applying Terraform configurations. Outputs are defined within Terraform configuration files to specify which attributes or values of resources should be exposed and made available for reference or use outside of Terraform. Let's look at a sample output configuration. On the left side, we have a resource block defining a subnet resource named example_subnet. On the right side, we have a resource block defining an OCI instance named example_instance. Here we use an output from the example_subnet resource for the subnet_id attribute, referencing it as OCI_core_subnet.example_subnet.id. By using outputs, we can dynamically link resources together. In this example, the instance resource references the subnet resource, allowing Terraform to manage dependencies and ensure resources are created in the correct order. Back on the left side, we have an output block that also references example_subnet. Used this way, this output will display the subnet ID after a configuration is applied and the resource is created, for summarizing purposes. This concludes our lesson on outputs. Thanks for watching, and see you in the next lesson. Hello and welcome. In this lesson, we will cover Terraform modules. Modules in Terraform are self-contained packages of Terraform configuration that are managed as a group. They enable you to encapsulate and reuse infrastructure components, making your configurations more modular and maintainable. Let's look at an example to understand how modules work. On the left side of the slide, we have a module file located on modules/compute-instance/main.tf. The modules directory is placed on the same directory as the root configuration file. First, we will define several variables such as instance_name, image_id, and subnet_id. These variables allow the module to accept inputs, making it flexible for different use cases. The resource block within the module defines the OCI instance named example_instance. It uses the variable from the configuration. On the right side of the slide, we have a main configuration file that uses the module we just defined. The module block in the main.tf file references the module located at modules-compute-instance. We provide values for the variables defined in the module, and those values will be used on the instance creation. Using modules, you can create a standardized set of configurations that can be reused across different parts of your infrastructure. This approach simplifies management and promotes consistency, as changes made within a module can be propagated to all instances where the module is used. By encapsulating your infrastructure components into modules, you can create more maintainable and scalable configurations. Thanks for watching and see you in the next lesson. Hello and welcome. In this lesson, we will look at the Terraform state file. Terraform state is a critical part of how Terraform operates. It keeps track of the infrastructure resources that Terraform manages. The state file, typically named terraform.tfstate, is used to map your configuration to real-world resources. On the right side of the slide, we see an example snippet of a Terraform state file. This JSON file includes various details such as version information, Terraform version, managed resources, and their attributes. Let's break down the key components and concepts related to the Terraform state file. Terraform states tracks the current state of your infrastructure. This includes information about the resources you've created, their configurations, and their dependencies. State files helps Terraform understand the dependencies between resources. This ensures resources are created, updated, or destroyed in the correct order. The state file contains detailed attributes of each resource. This includes configuration parameters, metadata, and any changes that have occurred since the resource was created. Terraform uses a state locking mechanism to prevent multiple operations from being performed on the same state file simultaneously. This is crucial for ensuring consistency and preventing conflicts when multiple users or systems are making changes to the infrastructure. The state file can contain sensitive data such as resource attributes and configuration details. It's important to handle the state file securely to protect this information from unauthorized access. Terraform supports storing state files remotely using backends such as OCI Object Storage Buckets, OCI Resource Manager, or HashiCorp Cloud. Remote state storage provides better security, collaboration, and disaster recovery capabilities. Understanding and managing Terraform state is essential for ensuring your infrastructure is correctly maintained and updated. By leveraging state tracking, dependency management, and secure storage policies, you can effectively manage your infrastructure as code. This is the last lesson of these modules, and a lot of concepts were introduced. Don't worry, in the next modules and lessons, when we start to practice writing and deploying configuration, the puzzle will start to take shape. Thanks for watching and see you in the next lesson. Hello and welcome. In this module, we will create your first Terraform configuration with OCI. In this lesson, before jumping on the Terraform configuration, we will show the basic setup required. This process typically includes downloading the appropriate Terraform package for your operating system, extracting the files, and adding the Terraform binary to your system's path environment variable for easy access from the command line. Once installed, you can verify the installation by entering Terraform version in your terminal or command prompt, which should display the installed Terraform version. Alternatively, if you are working with a cloud environment like Oracle Cloud Infrastructure, you can leverage Cloud Shell, a browser-based shell environment that comes with pre-configured with Terraform. Cloud Shell provides an easy, ready-to-use environment with Terraform configured and integrated with your OCI tenancy. In this course, the demos will use Cloud Shell to simplify for those that want to reproduce the steps on their environments. Before start writing the configuration, understanding the parameters evaluation order is crucial for proper configuration. Terraform checks parameter values in the following order. The Terraform configuration. It has the highest priority, directly specified in the provider block. Environment variables. Checked if it's not set in the configuration. For example, set OCI underscore tenants underscore OCID as an environment variable. Non-default profile in the OCI config file. Use it if not found in the environment variables. For example, you can have a profile called dev inside your OCI config file just for development. And finally, the default profile in the OCI config file as a failsafe. By following this evaluation order, you ensure accurate and efficient Terraform configurations for OCI. If you write the parameters inside the configuration file, the provider section will look like this. In the example, I mixed values and variables. No special reason, just because we can do that. Using Linux environment variables, this is how it will look like. You can either export the required authentication values as environment variables, or source them in different bash profiles when executing Terraform commands. If you primarily work in a single compartment, consider exporting the compartment OCID as an environment variable. The tenant's OCID is also the OCID of the root compartment, and it can be used where any compartment OCID is required. On Windows, this is how you can export the environment variables. When security token is used, your provider block can be as simple as this. Authenticating using security token is secure and effortless. The token expires after some time as a security measure. Even if you don't terminate the session, the expiration will get you covered. This concludes this lesson, and next we will write our first Terraform configuration. Thanks for watching, and see you in the next lesson. Hello and welcome. In this lesson, we will create our first Terraform configuration and navigate through the Terraform workflow. The Terraform workflow consists of the Terraform configuration file. In this step, you will define the infrastructure you want to deploy using a configuration file written in HashiCorp Configuration Language, HCL. This file specifies resources, variables, and providers. Step 2. Terraform init. Once your configuration file is ready, the next step is to initialize your Terraform environment using the terraform init command. This command sets up your working directory, downloads necessary provider plugins, and prepares your configuration for deployment. Step 3. Terraform plan. With your environment initialized, you can use the terraform plan command to create an execution plan. This command compares your configuration with the current state of your infrastructure and shows you what changes will be made without actually applying them. Step 4. After reviewing the execution plan, you can apply the changes using the terraform apply command. This command will create, update, or delete resources as specified in your configuration, bringing your infrastructure to the desired state. Step 5. Terraform destroy. When you need to tear down your infrastructure, you can use the terraform destroy command. This command destroys all the resources defined in your configuration, ensuring a clean environment. By following these 5 steps, you'll be able to efficiently manage and automate your infrastructure deployment with Terraform. In Terraform, all the configuration blocks can be placed in files with the TF extension. The first one is often named main.tf. This file contains the necessary configuration for your infrastructure, including provider settings, resource definitions, and other configurations. Later, we will show how multiple files can be used. For now, we will use a single file to allow to focus on other aspects. At this point, I will change to the OCI console and start my code editor. I already have a pre-created compartment called IAC that will be the target where I will create my resources. Starting the code editor, you just have to come to the developer tools, click on code editor. If it's the first time that you're accessing it, it's going to take some time to load, but after that is how it will look like. From here, I will create a directory. You can see the list of the files that are present in your home directory within Cloud Shell. And there I will create my IAC directory. In this IAC directory, I will have my first file called main.tf, and I will start to populate this file with my configuration. I have first my provider block with the required configuration. You can notice here that there are 4 lines that are commented out. These lines are commented out because we are using Cloud Shell. If you are not using Cloud Shell and you decide to do that on your local machine, you will have to uncomment this line and populate accordingly. If you decide to use the token authentication, it can be simpler than that. Now that we have the provider, let's add a block with the simplest resource that we could create within OCI, a VCN. So we will have the resource block, we will have the type of the resource, OCI_core_virtual_network, and the unique name within the configuration. Here you will have the compartment name. I will have to replace with the my compartment. And I already filled some of the parameters that are necessary to create the VCN, the CIDR block, the DNS label, and the display name. To get the compartment name, I will use a new tab and I will navigate Identity and Security, Compartments. Here's my IAC compartment. I'll copy the value and place that value in my configuration file. And with that, step 1 is done. We have our configuration file. I can come here, File, Save, and step 1 is ready. Now it's time to initialize my working environment. To do that, I will start a terminal, so I don't have to open a new window. And I will have access to Cloud Shell here. Currently, I'm not on the same directory, so I will change for my IAC directory. You can see here my main file. And let's start with Terraform init. It will download the required plugins, any required configuration that might be necessary to download as well. It will do that, and Terraform has successfully been initialized. If we take a look at the directory now, we will see the log file and we will see a .terraform directory. Inspecting this directory, we can see that the provider for OCI was downloaded. We can see the version, we can see all the files that are part of it. With that, we finished our second step with Terraform init. After running Terraform init, it's time to run Terraform plan. Terraform plan will load the configuration and show an action plan of what's going to be created, what's going to be deleted. You can see that here on the screen, and at the bottom we have a summary showing that we will create one resource, our VCN. There's nothing to be changed and nothing to be destroyed. You have the option to save that plan to a file, and when you run the apply, you can run the plan that you reviewed. But we're not going to save this, we're going to just run apply. and ignore the alert that it might not be the same plan. We have control of the environment, so it's not to be a problem. Let's clear the screen again. Terraform apply. We will see the same summary that we saw before, but now we have to enter yes as the action that we actually want to perform those actions, and voila, the resource was created. You can see that OCID was printed here, and if we check on our other tab, we can go to the Virtual Cloud Networks, and we have VCN1. If we check here the OCID, it ends on YRXA. We can check here. YRXA, the same VCN. Now, if we don't need that resource anymore, it will be time to destroy and finish the workflow that we have for Terraform. Let's clear again the screen, and now Terraform destroy. With Terraform destroy, it will read the state file and will create a plan of what needs to be destroyed, and adjusting the order and making sure that the environment is clean of what was created before with the configuration. Setting yes here, we will confirm our intent, and after running, it's good as gone. If we come back here to the other tab, Virtual Cloud Networks, that network is gone. With that, we conclude our first Terraform configuration. In the next lesson, we're going to check how we can create the same configuration using multiple files to making it easier to organize your environment. Thanks for watching, and see you in the next lesson.